Thanks a lot for participating in this webinar, which is the last of a series of 7 my department is organizing in these weeks. My name is Francesco Laio, and I'm here to chair this session. So why this cycle of 7 seminars? The US Academy of Sciences, Engineering and Medicine have recently identified 5 grand challenges and opportunities in environmental engineering for the next decades. We have been inspired by this analysis, and we have launched this series of webinars. The first 5 webinars have regarded the very same grand challenges that have been identified by the National Academy of Science. But these were not enough for us, because we believe that other expertise which is available in other departments, in particular regarding critical raw materials and energy transitions, would also have been very interesting for prospective environmental engineers and for people who are interested in the environment in general. This is the last webinar. We have talked in the previous webinars about climate change, about sustainable food supply, about the cities where we live in, about the pollution, that trying to think of a future without pollution. We have talked about critical raw materials, and with the webinars of tonight, we are closing with one of the most important challenges that is waiting for us in the next decades. So how can we, where can we get the energy that we need? So the title is Decarbonization, the heat is on. And this webinar has also been registered as part of the Energy Days, a series of side events organized all around the European Union in the framework of the EU Sustainable Energy Week that will take place between 22 and 26 of June under the theme Beyond the Crisis, Clean Energy for Green Recovery and Growth. We believe that our webinar stands very well in this under this theme, and this is why we have also registered in this initiative. So this is a very short abstract of what Francesca is going to talk about in a few seconds. The very broad issue is the one brought by climate change, which immediately refers to the energy challenge. So where can we get energy, and how can we move from traditional fossil fuels to renewable energy sources? You will see that Francesca will take a very pragmatic approach to the problem, and will try to tell us if these renewables are enough to cover the demand for energy of the world, and she will also spend some time to speak about the counter effects in economic and environmental terms that this transition might bring to our world. Our speaker is Francesca Verga. Francesca is a full professor of reservoir engineering at Politecnico. Over the years, she has been very active in research projects. She has a really impressive curriculum of important projects on reservoir engineering, natural gas storage, and energy transition. She has always taken a very pragmatic approach, leading to a strong impact of what she has done, not only in terms of knowledge advancement, but also in terms of impact on the society. So, Francesca, thanks a lot for accepting our invitation to give this seminar. The floor is yours.
Okay, thank you very much, Francesca, for your introduction. So thank you, everyone, for being here tonight. The topic we're going to discuss about is decarbonization. The heat is on. Why the heat is on? Because there's a lot of interest on this topic, and for very many good reasons. Now, no matter which energy outlook you may consider, they all highlight that there will be a need for energy, which is rapidly growing. and this is a fact we need to come to terms with. But at the same time, we would like to reduce the emissions of greenhouse gases, which are responsible or co-responsible for climate changes. So we have a challenge there, a challenge to meet this energy demand, but yet take care of the environment. Now, out of the global electricity use demand by sector, it is particularly interesting to note that the residential use is one of the trends highlighting the steepest increase. Now, we are faced with an energy dilemma. On the one hand, we would like to provide energy for all. And just to give you a figure, currently, there are still 850 million people around the world who lack access to electricity, but at the same time, really need to reduce emissions of carbon oxide and dioxide. So we want to go toward a major transformation of the global energy system to fight climate change and pollution. And this is in line with the energy-related components of the United Nations Sustainable Development Goals, which really have a strong point in promoting sustainable development and reducing emissions to fight climate change. But what really makes energy demand increase? Well, the growth in the world's population is the first answer. United Nations estimates that the world population will grow to nearly 10 billion people by 2050. Maybe this is a slightly high estimate, but we're not far from that, even if we consider that we're right now, 2020, close to 8 billion people. At the same time, we are observing a rapid urbanization. Currently, already 50% of the global population is urbanized. And again, the United Nations projects that by 2030, 60% of the global population will be urbanized, with the number of megacities also increasing to some 40. And megacities are defined cities with over 10 million inhabitants. Now, moving from the countryside or rural area to cities implies an increase in energy consumption. On the other hand, there is a correlation in between the energy demand and the economic growth. We can see that China, India in particular, are the two, well, probably not emerging countries, but definitely the countries having more substantial economic growth, and to them is associated most of the increase in energy demand. As you can see, the OECD countries, which basically are 37, only 37 member countries, and some key partners representing about 80% of the world trade and investment, have a forecast of a very slight increase in energy demand. The majority of energy demand comes from the other countries and mainly from Asia. So Asia will be responsible for this huge surge of energy demand, and unfortunately currently is also responsible for large emissions. Now, out of the very many outlook that forecast energy demand in the next decades, this BP energy outlook is particularly interesting because it shows a growing need for energy usage for buildings. And this, again, is in line with the other estimates from other sources, all identifying moving of people from rural environment to cities and megacities is one of the major factors contributing to an increased demand for electricity and energy more in general. And again, here it is confirmed that in particular China, but also India and other Asian countries with a minor contribution from Africa will be the countries that will demand for more energy. Now, what is decarbonization? Why do we speak about decarbonization? Because energy can be provided by many different sources. And what we would like to achieve, if not eliminate, is a reduction of the carbon intensity of the worldwide energy use. And the graph that is showing to the left-hand side, you see the impact on wood, coal, biodiesel, diesel, gasoline, and so on and so forth, and methane. And you see that we do not consider numbers in particular here, but we consider the trend. You see that the emissions of CO2 per kilowatt hour emitted by methane are really very, very small compared to the other type of fossil fuels, coal and wood. So a transition to methane is really desirable because it would by itself reduce significantly emissions. On the other hand, left-hand side of the slide, you see a graph showing the carbon intensity of electricity generation, comparing coal, oil, natural gas, and then a number of renewable energy sources. Solar photovoltaic, geothermal, solar concentrated solar energy production, biomass, nuclear, wind, ocean, hydro, and so on and so forth. Please note that methane would not be comparable to natural gas. So these different estimates not only come from different sources, but really are not entirely comparable directly. But in all cases, we can see that methane, so gas, really allows to reduce significantly emissions. Yet when this is compared to renewable sources, it still seems to have a high quantity of emissions. So it would be natural to say, well, then why do not we move to renewable energies? So I wanted to be a little bit provocative here, asking this question, but sustainable energy is really sustainable. Can we really afford as a society to entirely move to renewable energies? So here I offer you a case study, which is our country, Italy, and the electricity consumption per year in Italy is some 320 billion kilowatt hour. Now imagine that now we want to provide this energy entirely relying on solar power. The area needed for full conversion to solar energy under the assumption of ideal radiation would be approximately 10,000 square kilometers, which makes it 50% of Tuscany. Okay, we could do that, but at what cost? So one may think that wind energy is a better option. So let's repeat the exercise again for Italy. Again, electricity consumption remains the same, 320 billion kilowatt hour. The area needed for full conversion to wind energy, again under the assumption of ideal wind conditions, would be approximately 20,000 square kilometers, which make it 80% of Sicily. On the other hand, we may want to consider biomasses to substitute fuel consumptions for transportation. Now, to do that, the area that we would need to full conversion to biomass would be approximately 30,000 square kilometers, which makes it 62% of the whole plain. Now, this is obvious that it's undoable. So whether we look at solar energy, wind energy, or biomass fuel, these are not options which can right now replace current energy sources. This is not to say they should not be considered, but they're not yet a viable option to replace large or to provide large comply with large energy demand. So we need to find a combination of alternatives which eventually will allow us to have a real transition to a lower carbon use of fuels, of energy, and really reduce and mitigate climate change impact. Now, are we talking here about green or greener energy? Interestingly, the final report of the European Decarbonization Pathways Initiative, which was published toward the end of 2018, states that there is a trade-off between the extent of decarbonization and short-term emission reductions. In other words, they acknowledge that many zero carbon solutions are not yet market ready. And these same solutions will require substantial research and innovation funding to be implemented on a large scale, something that is not likely to happen for at least a decade. So in other words, even though this is where we want to go, the pathway leads to zero carbon solutions, we're not there yet. So if we want to truly do something to the benefit of the environment and the climate, we really need to go toward cheaper intermediate solutions which can bring down emissions in the short term. And the very same commission suggests the use of natural gas for this transition. They even say that zero carbon molecules have an important role to play, but due to efficiency considerations, they should be limited to cases that lack other decarbonization options. And they state that the obvious, that methane contains carbon, but also there are a different number of routes for producing gaseous fuels with minimal or even negative greenhouse gases emissions over the full life cycle. And one specific case that they mention, and it's very interesting, is zero carbon produced hydrogen together with captured CO2, CO2 captured from the atmosphere. Yes, we have to address climate change, but we also have to address pollution, which is one of the other key issues that we're faced with. So this slide shows yet another outlook about how the global energy mix might change in the next 20 years. And you can see that the increase of the different energy sources is relatively limited, except for renewables. Renewables really is increasing many times and contributing significantly to the transition. Yet, they will never be able to replace the use of fossil fuels, even in the next 20 years. Now, probably this is slightly pessimistic. Note that this data here come from the World Energy Outlook, but we have even more optimistic outlooks from the BP Energy Outlook, where renewables reach nearly or over 15% of the total share of primary energy. And at the same time, you see a decreasing trend for the use of gas, a decreasing for the use of oil, a decreasing trend for the use of coal as not entirely matching the other outlook, which kept the use of oil and coal rather constant, but they too show an increase in the use of gas, as slightly does, okay, or in percentage is lower than the increase of renewables, but still we're talking about significant figures, the outlook from the world energy source. So they both, with different numbers, reflect the same scenario: an increase in the use of natural gas, an increase in the use of renewables. Yet the component from renewables is still limited and will not be able to replace the use of gas. Something interesting comes from the agency, the US Agency for Energy, which shows the reduction of carbon emissions from a change in the fuel mix. Now, shifting from the use of other fossil fuels to natural gas had the positive effect of reducing natural gas related emissions more than other options of non-carbon related emissions could achieve. So in other words, the shift to natural gas was extremely beneficial in terms of emission reductions. In a way, this is encouraging, okay? If we want to look at the positive side, it's truly encouraging, because this means that we can work actively at changing the energy mix right now. We're already able to contribute to this goal. Now, this implies not only the use of natural gas, which is produced and currently being produced worldwide, but we can also move to green methane. We can move to generating methane through capturing CO2 from the atmosphere or from sources which generate CO2, putting it together with hydrogen, which can be generated, produced with green technologies, and obtain methane. What are the true horizons in this methanation process? Well, it would have a real benefit of reducing CO2 emissions in the atmosphere. However, for the process to become attractive at the industrial level, it requires availability of CO2 and H2 in industrial quantities. There's a whole lot of experiments running and being performed currently about how to make CO2 and hydrogen react, how the reaction can be optimized. However, this is done in the lab. Obviously, this is the starting point, but we're not ready yet for a large-scale deployment. What is the benefit of transforming hydrogen into methane? Why not using hydrogen as it is? Well, we could, we will, probably one day, but we're not ready. Again, we need to use infrastructures which are not there. We're not ready to use hydrogen, but we are ready to use methane. All the infrastructures are already existing, ready to go. We don't need to invest any further money. So this becomes attractive in economic terms and more doable. Then we have a further challenge that we have to face. We need to balance CO2 and H2 streams with fluctuating seasonal and daily energy demand, so methane demand. And this calls for energy storage. Okay, we know that we have a higher energy request during the winter season. Then we have a higher energy request during daylight hours. So the energy need will change over the day, over the seasons, depending also on the type of application, whether it's residential, whether it is for power generation. So how to combine a need which changes and a production which is not truly constant, as we will see in a second. We can partly address this issue through energy storage. Energy storage is the capture of energy produced at one time for use at a later time. Energy storage often involves converting energy, some forms that are difficult to store, electricity, for instance, to more conveniently or economically storable forms, a gas, for instance. Now, there's a lot of enthusiasm about lithium batteries, and this is totally understandable. However, we should not forget that lithium is a rare earth mineral. And you see the reserves by country, they're concentrated in Chile and Argentina and China, something in Australia, and that's it. Just minor percentages elsewhere in the world. But mostly you should consider the price of lithium, how it has increased significantly because of the request that is on the market. So it is not thinkable that we can store energy produced through renewables using batteries. We need to conceive something different, something smarter. Underground gas storage could be a solution, can be a solution. Where do we store typically already? We do that. Where do we store gas? In aquifers? We're talking about deep saline aquifers. Obviously, we're not talking about aquifers which would provide drinking water. Abandoned mines, salt cavities, where salt is dissolved on purpose to create a sort of cavity to contain the gas, or depleted reservoirs. And this is pretty ironic that we're using depleted reservoirs to store the energy that can be produced with green technologies. What are underground reservoirs and how do they look like? They're not caverns, okay? They are pores in the rock which are filled with the gas injected deep in the subsoil. And when we say deep in the subsoil, we're thinking about 1 kilometer or 2 perhaps below ground surface. So we inject the fluids through wells, we fill the pores of the rock, and the fluid is stored there for subsequent use. We have a relatively good knowledge of how to study, characterize, and simulate the behavior of these systems, because as I was telling you, this has a very long tradition, which comes in the beginning from the petroleum industry, but then has moved forward, because there is quite a significant experience in underground gas storage. If you think that the first application dates back 1915, when the first successful underground storage of natural gas was deployed in a depleted gas reservoir in Ontario, in Canada. And currently, we have nearly 700 facilities worldwide. We also have an experience about carbon capture and storage with the first facilities deployed in 1996 in Sleipner in Norway, and now having 18 large-scale operating facilities worldwide for carbon capture and storage. And we also have experience on hydrogen storage. In the 1980s, the first hydrogen storage in a salt cavern was successfully made in Texas. Currently, there are 6 operating, 3 in England, and I'm saying England, not UK, because they're truly in England, and 3 in the US. So this energy storage option could really help closing the loop in the power to gas approach. Wind and solar energy, we must remember, are intermittent by nature. So they provide energy which cannot be stored, but could be used to produce hydrogen through water electrolysis. So hydrogen could be stored geologically. It would be equivalent to store electricity. Only thing that it would be a lot more convenient from an economical standpoint and technically feasible, because we have the technology to do that right now. Then hydrogen and CO2 can be combined to produce green methane. CO2 as well can be stored geologically, and the shift has been shown a few years ago when CO2 was stored and intended as permanently sequestrated in the underground, where now CO2 is stored for subsequent use. So both hydrogen and CO2 would be readily available at industrial quantities. And so this could really become a technology which can help the transition toward a green energy scenario where renewables hopefully will make their way to become the primary energy sources. Thank you very much for your attention. I'll be very happy to answer any questions that you might have.
Thank you, Francesca. Very nice talk. Just a flash presentation by Valentina. Valentina Socco is the coordinator of our Board of Environmental Engineering. Can you tell us something about the what we have in our paths regarding these issues?
Thank you, Francesco. Thank you, everyone, for coming, and thank you, Francesca, for the enlightening talk. Well, actually, as Francesco said at the beginning, the idea of this series of webinars was exactly born in the occasion of our open days for future students, and it was aimed at providing a platform for discussion at high level to the real topic that are behind environmental engineering and resources engineering. In our education offer, after our bachelor program in environmental land engineering, we have two Master of Science program, one in environmental and land engineering as well, with 4 different paths. That ranges from climate change. We have an entirely taught in English track on climate change, which is the first in Europe in an engineering track that is fully dedicated to climate change. And then we have tracks in environmental protection, in natural hazard and risk management, and geoengineering. And then we have a resources engineering master degree, petroleum and mining master degree, in fact, where we have 2 tracks, one devoted to hydrocarbons and one devoted to mining engineering. And these tracks are characterized by a strong attention to environment and sustainability. Our content are continuously updated to respond to the need for energy transition, and there is a large offer of courses on environmental problems and sustainable industry and resources, and also renewable energies inside the track. So I will stay here for the question time session, and if there are any people who are interested in having information about our education program, I'll be glad to answer.
A couple of questions have already emerged in the chat. The first one regards smart energy systems. Lorcan is asking if you can add some more details on energy efficiency, storage, interconnection of and other elements of smart energy systems. So this component of the energy transition. Can you tell something about that?
I'm not sure that I fully grasp the question. Energy grid is not an alternative to energy storage. We can have energy grids, okay, but we'll still need to use the excess electricity generated by intermittent sources.
I guess what he's asking if the efficiency of the whole energy system might be improved by adopting smart energy systems, and this would also be a way to reduce our need for energy, of course, if you improve the efficiency of the whole system.
Absolutely, absolutely. Yes, obviously the improving efficiency, again, we're not saying that we should not improve efficiency or that anything that can be done to have a better use of energy should not be pursued. The problem is that we're probably comparing different scales of problems. Okay, there is a huge energy demand which need to be addressed. And even increasing efficiency, which can be absolutely beneficial, would not offset the energy demand. So I think we have to work on both aspects of the issue.
Okay, the second question from Saad is pertaining with the storage issue, and he's is suggesting that depleted reservoirs cost less and might be a good option. What do you think about this?
No, this is absolutely true. Depleted reservoirs are very well-known systems. Typically, they have in between 20 to 40 years of previous history. And so they're very well characterized and safe. We should not forget safety issues and public acceptance, which is also important. So definitely they're a very viable option. And this is not, I mean, it is confirmed by the fact that probably 2/3 of the gas storages are actually into depleted reservoirs.
Thank you. So I also have a question for you. I totally agree with your pragmatic approach, but I would ask you if you believe that in some way this the manner how we speak about these things might also influence the society around us. What I mean is that of course we have to somehow also dream about renewables and about new technologies and about a future where the emissions will be much lower than today. I guess as engineers we have the need to tell the truth, and so to also say that some of these things may not get real, but I'm not sure that about what the system in this moment need. I'm not even sure if my question was was easy to understand, but maybe you can try to answer.
Okay. Your concern is that saying that we have one solution might totally make lose attention to other more virtuous solutions. I don't think this is the case, because I think that it's simply to be able to react now rather than waiting for an ideal solution which we do not have and is not likely to be available in the next future. I mean, I live on the same earth as anyone else, so I'm the first one to be wishing in a solution allowing us to have energy and reducing or actually going to zero in terms of pollution and greenhouse gases emissions. But we're not there. So do we want to be daydreamer and pretend that we can have a solar panel on our roof and this will solve the problems of the world? Or do we want to take a more practical approach and say, okay, this is part of the solution, part of the energy mix, but this is not sufficient. Yes. So if we want to take action, we need to do what it takes. At the same time, this is a transition. This is not the goal, it's a transition, it's the energy transition period. And we needed to be able to put together the different sources. And the more renewables we have, the better it is. But if this is only able to satisfy 15% of energy demand, the question is, do we want to use coal or something cleaner and greener? Not
very
clean, not
very
green.
clear, very clear. My point was only that, but I'm sure you fully agree. The point is only that this should not stop the investments in innovation technology in renewables, but I'm completely sure that you fully agree with that.
Absolutely so.
A couple of other questions. Alessandro is asking if there is any plan for the storage reservoirs in Italy on the horizon.
Yes, there is. Studies are underway, yes.
Other details? Any other details you can give to the audience, or this is?
No, they are still in the design phase. So honestly, it's not that I don't want to, it's that details are not available. Companies are working intensively on identifying possible storage sites for addressing once more the energy challenge in this transition phase. But of course, only after the ministry will say its final word, and then data will be public and it will be official. But I know that there's a lot of let me make a joke. There's a lot of energy going in this thing.
Okay. Enrico is asking if you think that the transport sector should also transition to methane. So if the transition should also regard the transport sector itself, not only electricity production but also transports.
Probably I'm not the best, the most qualified person to answer that, because I'm not really into transportation. So I don't know what is the optimal solution for transportation. And my point was that transition from carbon and oil to methane is certainly beneficial. Then what is the optimal option for transportation? Please let me skip this one.
Kalik is asking if what do you think is the reason behind the lack of interest in underground storage? Do you think might be due to a lack of technological solutions or lack of economical motivation?
A lack of interest in which type of storages?
Underground storage.
No, I don't really subscribe entirely this question, because there are storages operating in aquifers, deep saline aquifers, storages operating in salt caverns. So all types that I mentioned in the presentations are used. Obviously, it also depends on the geological underground that every country has. So if a country doesn't have any, say, depleted reservoir, cannot use it, or other countries don't have saline formations in which they can create caverns. So everyone has to come to compromise with what they truly have in their own underground, depending on geology. And this is not a choice, it's something that we have.
Salvatore is asking a question which might also have applied to other seminars that we had in this series. He is asking if there is any strategic plan with the European Union involving also Italy to invest in technologies related to rare earth elements. Terre rare.
Yeah, no, I heard it, but I don't know. There are actually, no, not true. Because we, as Politecnico, we're involved in a European project about batteries. So yes, there is currently a research project about batteries. But to be honest, I'm not an expert on batteries and lithium. So I don't know about other initiatives which might be promoted by the European.
If I may add something about these questions, there are also programs of European Union which are fostering sustainable exploration and development of new and environmentally friendly mining plants, and certainly rare earths are one of the focus. So battery metal in general, let's say. So Politecnico, for instance, is involved in one of those networks, which is Smart Exploration. You can finally find it on the web. And there are several initiatives of EU, but I'm talking about resources here, not about technologies.
Okay, the next question is from Valentina. So you have the microphone on. Please go ahead.
No, I think that it is also important to understand which are the competencies, according to you, Francesca, who are needed for the next 10 years to face and to tackle these issues.
Okay, the answer is which one, because obviously you need to be a chemist to tackle the problem of hydrogen generation. Also, to make the reaction between CO2 and hydrogen occur to generate green methane is easier said than done. Okay, so there's a lot of research ongoing. But then when it comes to storage, there's definitely a need of competencies related to reservoir engineering. So to the ability to characterize and quantify, characterize the site and the potential storage, quantify how much gas can be stored, how can be injected and produced back. So this is a transition in the competencies as well of historical professionals from the oil industry, which are now looking at the same disciplines with a totally different type of view, different eyes, but the problem remains. And we, instead of battling them, we should take advantage of their competencies.
Thank you, Francesca. While I leave some seconds for other questions to emerge in the chat, let me tell you that this, as I told you at the very beginning, this is the last seminar of a series of 7 we had in the last couple of weeks, and as the department head, but also Valentina as the coordinator of the Educational Board of Environmental Engineering, we are very happy about the audience that we had in these webinars, and so let me thank you again, those of you who are here for the first time, and those of you who have been here for many of our webinars. We are so happy of this series that we believe we could be back to you with others in the next few months. So please stay tuned with our department. If you have missed some of the other webinars, if you are interested in the topics that have been treated, the webinars are online. The website has been now posted on the chat. One more question: is there a possibility to do it in a smaller scale, down to household size, for instance? What do you mean? This what? Storage? Diogo, might you please directly pose your question or explain a little bit better? Storage and transformation. Okay.
No, well, underground storage locally, no, not doable, because we need to find geological formations which are adequate for fluid storage, and typically, as I said, it's a kilometer or 2 below the subsurface. So, and also the cost of reaching these formations are extremely high. So it's not something that could be done by individuals. This has to be an effort from the society as a whole. The investments involved are not prohibitive, but definitely too large for individuals.
So, Thanks a lot again, Francesca. It was really interesting. And thanks a lot to all of you who are still there, notwithstanding we are at 7 p.m. at least in Italy of Friday night. So thanks a lot to you all, and see you again in other webinars that we will organize in the future. Ciao.
Thank you.
Thanks a lot.
Thank you very much, everyone. Thank you for your attention. Thank you.